Hello once again. Still got my smooth jazz playing, and wanted to talk some more about physics and mathematics, just kind of casual conversation. Um, so I think it's kind of interesting to take and apply calculus to physics. So let's do some of that. Basically, how do I want to do this? All right, so work equals. That's kind of funky looking. Work equals force times distance, right? Or work equals integral from something to something of force times ds, where s is the distance. So these are both vector quantities. So it's f dot ds, and here this is going to be s initial to s final. Kind of sloppy there, but so work equals the integral from s initial to s final of f dot ds. This would be if the position is, see how to say this, if it's changing, I want to say if the force and the distance are not directly moving in the same direction. So for example, if your force vector is pointing this way and your displacement vector is pointing this way, then you're going to want to use this. You can't just say force times distance. What else? If let's say this is your force vector, but let's say that your displacement vector goes like this. I'll call it S. So it changes with respect to time, as far as the direction of it changes with respect to time. So in this case, you would also have to use this integral. Another possibility would be if you may also have work equals integral of s, the displacement vector. I think this should still be dot df. So, and then this would be from force initial to force final. This would be true if, let's say, your position vector was straight, was consistent, but your force vector, went like this over time. So your force vector is not constant, but changes in some regular fashion. So pretty sure this is correct, even though I haven't seen it written anywhere. But for now, let's just go with the first one. Yeah, let's do this. Okay, so work equals, let's actually rewrite that anyway, that's sloppy as all get out. So we have work equals the integral from the initial position to the final position of our force vector dot ds. And let's say, so some examples of this, I have one that I've recorded in, I think, more than one video now, actually, is if you have this, this is a tall building, little pulley here. Pulley's not usually drawn, but I think it makes it a little nicer to think about. Some rope. I kind of drew an object on the end. Let's say there's no object on the end. We're just considering the weight of the rope. It's a heavy rope. It doesn't have to be a heavy rope, but it's easier to imagine it properly if you think of it as a heavy rope. Some guys up here pulling on this rope. As he pulls on this rope, there's work being done. Well, in this case, we would say that work equals force times distance, except in this case, the force is changing. And actually, you know what? Maybe that second equation was wrong, because here we still use the integral. We still consider ds, even though it's the force that's changing. But I guess it's changing over the interval, of the displacement. So what I mean by that is, when the rope is this far down, force to pull up the end of the rope here to this point here is going to be m times g. Is that right? M times g times, yeah, so that's the force. The force isn't changing, it is the distance that's changing. My mistake. So at this point, the distance is going to be this amount of weight right here times the distance from here to here. But if we take another point up here, the work required to pull this piece up is the the weight of this piece times the distance of this piece. So that's the weight from here to the distance here. The same here, the weight from here to the distance here. And what you could do to calculate the full work for this rope is calculate the weight at each point, and then calculate, well, you could calculate the weight at each point times the distance at each point, and then sum all those. Or alternatively, you could calculate the weight at each point, which is the force, times the distance is summed. So d1, I used s, so let's stick with s. S1 for displacement plus S2 plus S3 plus S4, etc. And this is actually what you would have to do to find the work. And this is the integral. So work equals the integral of S initial to S final of force dot ds, where ds is the tiny little piece of the distance, the displacement for the tiny little piece of rope. So it would be like S1, for example, or S2, or S3, or S4. So that is one way to apply calculus to work, to calculating work. Let's take another way. So what is, I'm trying to blank. So work equals So actually I think this would be the same for charge, but in this system, force equals mass times g, mass times acceleration. And in an electrical system, force equals the charge times the electric field. So if we have work equals force times distance or displacement, and then we have an electrical system, we would say work equals charge times the electric field times the displacement. And this setup is assuming that the electric field and the displacement are in the same direction, and that the electric field and the charge are constant over that displacement. So let's say you had some situation where there's a charge and this charge displaces. So let's say that it moves from here to here. So this is S initial. This is S final. And let's say that there's an electric field. Let's just say right now that the electric field is caused by two plates of a capacitor. So that we'll make this positive. This is negative. The electric field, I'll use different colors here. The electric field points downward because it flows from the positive plate to the negative plate. Okay. This is our electric field. Now let's say our force, in this case, that this charge is going to feel will be a force also downward. And it will feel it the whole way as it travels. Which actually technically, so if this is the displacement vector, how do I want to say this? Conceptually, I think I'm correct to say that if our displacement vector goes this way, and our force vector is a constant this way. I'm going to draw this like this, but this is not exactly right because they're not being added. So let's say this is our displacement vector. If this is our force vector, then in order to reach this path, I believe it's correct to say we have to have an acceleration vector that points in this direction. That seems like that should be correct, and except these are, I drew it as though they're added. I don't believe that they should be added, but the directions I think would point like this. I don't believe that I accurately sketched the magnitudes. That seems true. Otherwise, let's think for a second. If this charge flows across here, but feels a downward force, and yet does not move downward, so force equals mass times acceleration. Now, if, let's say that our object had, oh, you know what it is? There should be a second force here. That's the problem. In my first picture on the top, there would have to be another force going like this. Without this other force, then my initial picture is wrong. That's the problem. So this is some unknown force. I'll just put a question mark to make this picture. If we don't have that picture, then it's going to follow the path of projectile motion. So let's get rid of some of this stuff here. All right. So let's redraw this out here. Let's say that we have these two capacitor plates. This one's positive, just because I want it to be. And this one's negative. And let's say that we have some charge. Let's say it starts up here. Let's say it follows this path right like that and ends down here. Now, so this path is the displacement. And let's say this is S initial. And let's say this is S final for initial position and final position. And let's put in some forces. So let's say that we had an initial velocity, right? We use green for this, I guess. So there's some initial velocity that's moving directly horizontal, kind of like what you would see in a projectile motion problem. There's this initial velocity, and I'm gonna end up probably using too many colors here, but there's no force. There was just happened to be there was a force in in the past or whatever. So this reached equilibrium and it kept moving and moving and moving and moving from somewhere here off in unknown land with a constant velocity. Oops. And when it hits this point right here, it starts to feel a force. Let's use this color. The force is a force that should be, that's not drawn very well. So there's a force that points down perpendicular, it should be, from the positive plate to the negative plate. I don't know, force, I think force is the right word. It's a field, the electric field. So it points like this. So once this charge hits this position right here, its displacement is no longer directly linear as it had been, because it starts to feel this force pushing from this positive plate to this negative plate. And so I can draw that force. The force is directly in this direction here, same as the electric field, because this is a positive charge. Had this been a negative charge, the force would be directed in the opposite direction as the electric field. Okay, what next? So, so in this case, let's say we wanted to calculate some work. We have work equals the integral from the initial position to the final position of force dot ds. So what this is saying is we're going to take this force at every point along this path, so that at any point on this path, so let's say maybe this position right here represents our ds, our tiny little piece of our displacement. Which is still technically a vector. So ds would be this tiny little arrow pointing in this direction, infinitesimally small arrow that I've highlighted right here. You can imagine this is one giant curvy arrow or a series of little straight arrows. And what we're going to do is we're going to calculate the force, we're going to calculate the work at this position. So at this little position right here, work equals F dot ds. So it's going to be the force times the position vector. And in this case, these are both vectors, and what we're going to use is dot product multiplication. So it would be the force dot ds, which happens to be, we're not going to actually use this, but mathematically that's the same as, it should be f, I think it would be fs cosine theta, if I didn't mess that up from my memory. But we're actually not going to use that, but we could. And we could use that at every little point on here and calculate the work at every little point, add all the work, add all the pieces of work up to get a total value for work. And if we were to do that by approximation, you could use fs cosine theta to figure out f dot ds. But we're not going to do that. Instead, we're going to turn it into an integral, because to integrate means to add up each of these ds's. Yeah, so if we want to flesh this out a little further, work equals integral from s initial to s final of the electric field, which is a vector, times the charge. I guess you'd still put dot here. Yeah, dot ds. So now we can ask some more questions. Is the electric field changing? Well, and the problem that I set up, no, the electric field does not change. I suppose if you had, this hasn't been confirmed for me, but you know, assuming I'm not mistaken for some reason that's beyond my understanding. Let's say you had a plate like this and a plate like this, then I'm not actually sure. I believe, color I use purple. I believe the electric field should still point like this. What is E equal to? Just think about this for a second. So this is still the electric field. This is supposed to be noticeably longer than this. I actually drew it so sloppy that it almost looked the same length, but I think it was, let's see, so force equals K Q1 Q2 for R squared, and force also equals E times Q. So we have, I don't know which charge that is. I'm missing something. I know what it is. So E equals F over Q, which means that E equals K1, K, Q1, Q2 over R squared over Q. I don't think this is the right line of reasoning, because I don't know which Q that would be. Anyway, scrap that last little part. There's something that I'm missing in my reasoning there. So at any rate, going back to the problem, I believe that there is probably a way so that the electric field is not constant. Perhaps the way would be to say if this side has a lot more charges and this side has less charge, I believe that should change the electric field strength, but that's not the situation that we're trying to look at right now anyway. So for our current situation, the electric field is constant. As this charge travels along this path, the electric field is constant. So since it is constant, we could pull that outside. And the charge, I suppose you could imagine some kind of crazy hypothetical situation where the charge changes as it moves through this path. I don't know, maybe it's dissolving or evaporating or something, phasing out of existence. I don't know what's possible there, or if anything's possible, but let's say that could happen. We're not thinking that that's happening in this case. The charge is constant as it travels through there, so we can actually pull those out of the integral. So we have work equals E times Q times the integral from S initial to S final of ds. So this is just going to be work equals E times Q times S was our variable, going from S initial to S final. And when we plug those in, we're going to have work equals E times Q times S final minus S initial. And final minus initial is otherwise known as change in position. So like the change in. So we can also say this is the same as work equals E Q delta S. So this formula now should give you the work done in this, so long as I didn't make any mistakes. And if that's correct, then let's say that we had some values here. Let's say that we know the work. So work should be joules. I think it's still joules in this scenario, so we're going to call it joules. So let's say it was, I have no idea what a good number would be. Let's just say it's 10 joules. Switch my color here. So let's say we have work equals 10 joules. Let's say that the electric field equals, what are my units for electric field? Let's go back here. Force, so F equals E times Q. Q is in coulombs. Force is in newtons, so newtons equals something times coulombs. This is going to have to be in newtons per coulomb. Newtons equals newtons per coulomb times coulomb, so that they cancel. Alright, so the electric field should be in newtons per coulomb. So let's say we have 2 newtons per coulomb. Again, I have no idea whether these numbers are sensical or not, but just throw in some numbers. And our change in position, in this case, we're only thinking, so it should be, the way that I set this up, the change in position is going to be actually the distance from here to here. Technically, I also could have meant, so I have these 2 points. I could be considering the distance from here to here, which I'm not in this setup. I could be considering the distance from here to here, or I could be considering the distance along the diagonal, or I could be considering the length of this curve, right? Those will all be different values. And it should be, if my understanding is correct, because I think, let's see how to say this. I believe because the way I reduce this, I made the assumption during reducing, accidentally actually, that the electric field and the change in position were in the same direction. So technically the problem that I have set up is actually, well, the problem that I've solved for, I believe, would be, yeah, these 2 plates. And you had this charge, and the charge started at rest, and you let it go, and it changed position. I believe that is actually what my equation will find. So we're gonna go with that real quick. And all right, so let's say we wanted to find the charge. So let's say we want to find the change in position. Yeah, I think we can go with that. So now let's say we want to find charge. I like that better. So let's say we don't know the charge. So Q is unknown. And let's say that delta S equals, I want to make the math easier on myself, so I will say it's 1 meter, even though that's pretty, I know that's really, really ridiculous, but oops. I just want to make the math easier. It would probably be nanometers, but delta S equals, we'll do it. We'll say it's 1 times 10 to the negative 9 meters, 1 nanometer. All right, let's get rid of my sketchy stuff right here. Now, so this is what we know, and we want to solve for Q using the equation that I used in integral to derive. We're going to say that charge equals work divided by the magnitude of the electric field. The reason that I'm doing that is because I'm assuming that it's in the same direction as the change in position, times change in position. So the charge equals, we have 10 joules. Once again, I'm just going to assume the units were correct. I should have spent more time memorizing units, and I did not. So 2 newtons per coulomb times 10, oops, 10 to the negative 9 meters. I didn't write the units there. We'll just leave the units off for now. So obviously it's better to include them, but not 100% certain on my units here anyway, so. Alright, so this is going to equal 10 divided by 2 is 5. So we have 5 times 10 to the 9th and this should be coulombs. So this was our charge. That feels wrong. I think I picked really, really funky numbers, but just go with it for now. So, yeah, so we had this charge, right? And this charge, this graphic here more accurately represents what I just found. So technically this graphic is also true if we're considering change in position to mean vertical change in position only. So if this object sits here and starts at rest and falls, 1 times 10 to the negative 9 meters, and if it does 10 joules work while falling 1 times 10 to the negative 9 meters in an electric field that has a strength of 2 newtons per coulomb, then we know the charge on that charge. We'll just say particle. Maybe it's not a particle, but the charge of that object. The charge of that object must be 5 times 10 to the 9 coulombs. Now, there's some other ways this could have been solved, or some other calculations that could have been done. So let's take energy, for example. Let me switch to a new color to kind of help keep the things separated here. So now we're going to deal with energy. So we have, going from this graphic now, again, it would still apply to this graphic if we're only thinking of the horizontal component of the position vector. So, sorry, vertical. If we're only thinking of the vertical component of the position vector. So let's say that we have energy equals the energy initial plus, sorry, potential initial plus kinetic initial equals potential final plus kinetic final. And in this case, in either one of these examples, as long as in the first setup we're only considering the vertical component, or in the second setup where we consider it starts at rest and then we drop it, we should be able to use this to also find some similar stuff, I think. Except let's see what happens when I try to plug stuff in. So our kinetic initial is 0. It's 0. And it's 0 in both. And the reason it's 0 in this one is because it starts from rest. The reason it's 0 in this one, even though I imagine the charged object moving initially, it is moving 100% horizontal, and it is initially moving 0% of it is moving in the vertical. The final, I don't actually know when this stops. I don't believe that it hits the plate, so let's assume that it didn't hit the plate. And if that's true, once again, in both cases, even though here I drew it as though it hit the plate, I don't actually know that from the information that I gave. So let's say if it doesn't hit the plate, then we're going to have both potential energy and kinetic energy in the final. So I don't know if we're going to have enough stuff to solve, but let's just plug in some stuff and see what happens. So the potential energy initial is going to be equal to K. I want to say it's K Q1 Q2 over R plus 0 equals, and here the charges, I don't know if that's right though, because we only have one charge. Something's not right there because I only have one charge. What's the charge of this? Maybe you would have to know the charge of this plate. Let me keep going. I think so. This is going to be the distance initial, and then we have K Q1 Q2 over R final. plus 1/2 mass times velocity final squared. So yeah, with the information that I was given, we can't get very much between the two because items that I do not have to fill in for the second one, I know K is a constant, and it's 8.99 times 10 to the 9th. Oh, I think it's newtons times meters squared, coulombs squared. I'm more certain about the number value than I am the units. Charge 1, we know that that's what I just calculated right here. 5 times 10 to the 9th coulombs. That is the charge of the particle that is traveling. Now, charge 2 we do not know. That would be the charge of the plate. In fact, I don't think it matters which plate you use. In fact, if it's a capacitor, the plates actually have the same charge. So this is charge of plate, either plate. Oops, plate. Then what's next? our initial. This is unknown. This is the starting. Actually, let's pick a plate because technically it doesn't matter which plate, but the R and Q2 should both be the same reference point. So let's say this is the negative, let's say the bottom plate, the negatively charged plate. The bottom plate. And then let's say that R initial is also unknown. That is the distance, the vertical distance between the bottom plate and the charge. We'll just say vertical distance to bottom plate. Initially, and let's go with our final, also unknown, which is going to be the vertical distance to the bottom plate final. Just put some quotes and say final. And then what else is unknown? The mass was actually unknown. This is going to be the mass of our object. Maybe it's proton, maybe it's not. I don't know. So mass of, I'll call it a particle, even though it doesn't have to be a particle, but charge object. And velocity final is also unknown, so there's a lot of unknowns here. Velocity final equals, in this case, this is the final velocity of the particle. And in the first picture, I made it look like it hits the plate and perhaps it stops, but we don't actually know that from the information that was given. So this is the final velocity of the particle. We also could have used kinematics. So let me get some space here and see how our kinematic equations might have related to all of this. Maybe I'll keep that down there. So let's find some kinematic stuff. So kinematics are I like to use x's here, but it doesn't have to be in the x direction. It's just easier for me to memorize. So the final position equals the initial position plus the initial velocity times time plus 1/2 acceleration squared. That's one of them. Another one is velocity final equals velocity initial plus acceleration times time. Another one is velocity final squared equals velocity initial squared plus I think it's 2 times delta x, or the change in position. Pretty sure that's right. I might be missing something, but should be able to test that out. So yeah, anyway, I'm pretty sure those are correct. So these are kinematic equations. So let's say, all right, we don't know velocity initial, and in this particular setup there was an initial velocity, but we actually don't know the displacement in this graph either. We might be able to figure out the time, but we don't. Let's see, we don't know velocity final, we don't know velocity initial. Acceleration, so force equals mass times acceleration. We do know the force, I think. Where'd that go? Or we should be able to figure out the force. So let's say force equals mass times acceleration, or which equals the electric field times the charge. So we do have the electric field, we do now have the charge. So force, I should probably write it up here. Force equals the electric field times the charge, which equals 2 times 5 times 10 to the 9th coulombs. I didn't write the units for the other one, but 10 to the 9th. So this is going to equal 10 times 10 to the 9th. Force is in newtons. So we do have the force, so we could, I think this force should relate the same for this force. So we would, if we knew the mass, we could figure out the acceleration, but we do not know the mass. So what else? How else could we find? I think that's the only way we could find. We could find acceleration from, I think that's the only way we could find acceleration. So what do we have here? Well, we could find the velocity final from this, assuming that I got that. That's the only one I wasn't sure of. Let me check to make sure I got that correct. There's acceleration in there. I thought it didn't look right. Okay. So this one, 2 times acceleration times the change in position. They all have to have acceleration. That's kind of the point. Acceleration, change in position. So, okay. So we actually cannot use that then because we don't have the acceleration, and we don't have the initial velocity. Well, we don't have the final velocity. We do have the initial velocity in the y direction. We just don't have the final velocity in the y direction. And yeah, the first one, we don't have the time, we don't have the acceleration. So yeah, I don't really think we can calculate too much more without giving some more initial conditions, but there we go. There's a look at a physics problem.